We present LASR, learning articulated shape reconstruction from a monocular video. Our goal is to recover the articulated 3D shape of an unknown object from a video. This is an under-constrained problem. From limited 2D data, there exist multiple interpretations of the 3D object's shape and motion. To deal with this challenge, previous work often relies on strong category-specific priors in the form of parametric shape models or shape templates, such as SMPL for human, SMAL for quadrupeds, and recent category-specific mesh reconstruction methods. However, in the world of SLAM and structure from motion, rigid structures can be recovered without strong shape priors by instead relying on data likelihoods extracted from multi-view images. We exploit the intermediate regime between these two extremes. Specifically, we introduce LASR, a method for learning articulated shape reconstructions from a single video without relying on category-level template priors. Motivated by recent progress in differentiable rendering and self-supervised shape learning, we cast the articulated 3D estimation problem as an analysis by synthesis task. We solved the inverse graphics problem of recovering the articulated object shape and the camera parameters to fit video observations, such as object silhouette, raw pixels, and optical flow fields. Despite the under-constrained nature of the problem, we hypothesized that by providing rich video measurements, the articulated shape under blend skinning and camera parameters can be solved up to scale. First, we introduced the parameterizations of shape, articulation, and camera projection. To represent a 3D object, we use a triangular mesh with vertex colors. It is initialized as a sphere and optimized directly on the test video. Instead of modeling deformations from a rest shape by independently displacing each mesh vertex, we deform a fixed number of rigid bones. Each bone can be translated and rotated from its rest position. We visualize bones by a colored dot representing its centroid. Mesh vertices are represented with a linear blend skinning model where the skinning weights are visualized on the top left. Our skinning model allows vertices to deform as the bones deform. Skinning weights are parameterized by a mixture of 3D Gaussians with position, orientation, and scales. On the right side, we visualize the vertex motion controlled by one bone. The forward synthesis model transforms a pair of articulated shapes to the camera coordinates and performs a perspective projection. We use the soft rasterizer to render color images, object silhouettes, and forward-backward optical flow maps. To provide supervision to the system, we extract the raw pixels, object silhouette, and optical flow from a video. The silhouette can be either annotated or provided by an object detector, such as a point rend. Optical flow is computed using an off-the-shelf flow network trained on a mixture of synthetic and real datasets. Reconstruction losses are constructed to update model parameters by comparing renderings against the video measurements. We use common shape and motion regularizers that encourage smooth shapes, as rigid as possible deformation, least motion, and temporal smoothness of camera motion and articulation. Importantly, we introduce a soft symmetry loss that encourages symmetric shape and skinning weights. Instead of directly optimizing camera and bone transformations to minimize reconstruction error, we optimize the parameters of a convnet that predicts camera and bone transformations from an input frame. We find this results in a smoother optimization surface for analysis by synthesis tasks. To achieve high-quality reconstructions, we design a coarse-defined procedure that gradually increases the number of vertices M and the number of bones B. Here, we visualize the coarse-defined optimization of the articulated shape. At stage 0, only the camera parameters and the rest shape are optimized. In subsequent stages, we additionally optimize the skinning weights and the bone transformations. Between stages, we remesh to reduce artifacts, increase the number of vertices, and gradually refine the shape. Compared with model-based methods, our method does not require a 3D shape template or category prior, and is able to reconstruct outlier data more faithfully, such as the close marked by the red rectangle. Compared with category-specific mesh reconstruction methods, our method does not rely on category-specific training data or shape template, and therefore is able to reconstruct the shape of novel objects and objects with unknown categories. Prior-based approaches struggle to model the two humps of the camel, while LASR captures this subtlety. Our method is applicable to rigid or near-rigid objects. Compared with structure from motion methods such as CoLMAP, our method recovers a complete 3D shape and recovers the near-rigid structures such as slowly moving humans. Since our method does not rely on shape template or category priors, it is generic and applies to a wider range of object categories. In summary, we present LASR, a method for articulated shape reconstruction from a monocular video without using templates or a category prior. It uses two-frame optical flow to overcome the inherent incompleteness of non-rigid structure and motion estimation, and automatically recovers an articulated 3D shape under the blend skinning model. It achieves comparable performance with model-based methods and also applies to generic object categories. Thank you for watching the video.